Hello there, and welcome to another gentle journey through the cosmos, where mysteries float like distant stars and questions drift softly through the vast expanse of space. Tonight, we're embarking on a peaceful exploration of one of the most intriguing puzzles in modern astronomy, a tale that weaves together a famous radio signal from the past and an unexpected visitor from the depths of interstellar space. I'm curious to know where you're listening from tonight, and what time it is in your corner of the world. Perhaps you're settling in after a long day, ready to let your mind wander among the stars. If this gentle voyage through cosmic mysteries brings you comfort or sparks your curiosity, I'd be grateful if you'd consider giving this video a like and maybe subscribing. It helps this quiet corner of astronomical wonder reach others who might need a peaceful moment to contemplate the universe's deepest secrets. Now, I do hope this isn't so fascinating that it keeps you awake, but if it does, at least you'll drift off knowing a bit more about the extraordinary dance between radio waves and cosmic wanderers. So settle in, take a deep breath, and let's begin this story of signals, comets, and the endless search for answers in the darkness between worlds. Our tale begins on a warm summer evening in August 1977, when the universe whispered something extraordinary into the ears of humanity. It was a whisper so faint, so brief, that it lasted only 72 seconds. Yet in those fleeting moments, a signal traveled across the cosmos and touched down at a radio telescope in Ohio, carrying with it one of the most enduring mysteries in the history of our search for life beyond Earth. The Big Ear Radio Telescope, operated by Ohio State University, was a monument to human curiosity. Picture, if you will, a vast metallic ear pressed against the cosmos, listening patiently for any sound that might suggest we are not alone. Night after night, it swept its electronic gaze across the heavens, recording the natural radio chatter of stars, galaxies, and the cosmic background radiation that fills the universe like a gentle hum. But on August 15th, something different happened. As the Earth turned and the Big Ear's field of view swept across the constellation Sagittarius, the telescope detected a signal unlike anything it had ever recorded. This wasn't the random noise of cosmic radiation or the steady pulse of a known astronomical object. This was something focused, something deliberate, something that seemed to call out from the depths of space with an intensity that made the equipment take notice. The signal arrived at precisely 1420.4556 MHz, a frequency that holds special significance in the search for extraterrestrial intelligence. This is the natural emission frequency of hydrogen, the most abundant element in the universe, and the frequency that scientists had long theorized would be a logical choice for any civilization attempting to communicate across interstellar distances. It's a cosmic calling card, written in the language of physics itself. For 72 seconds, the signal blazed across the radio spectrum with an intensity between 54 and 212 Jansky units. To put this in perspective, imagine a lighthouse beam cutting through cosmic fog, bright enough to be detected across vast distances, yet narrow enough to suggest it wasn't just random stellar noise. The signal was remarkably focused, confined to a bandwidth of less than 10 kHz, like a perfectly tuned note in the symphony of space. But here's where our story becomes even more intriguing. The signal wasn't discovered immediately. It was astronomer Jerry Amon who, several days later, was reviewing the computer printouts from that August night when he noticed something extraordinary. There, printed on the continuous paper that recorded the telescope's observations, was a sequence of characters that represented signal intensity: 6, E, Q, U, J, 5. The intensity had spiked so dramatically that the computer had run out of numbers and moved into letters to represent the strength of the detection. Amon circled this sequence and wrote a single word beside it in red ink: "Wow." And with that simple exclamation, one of astronomy's greatest mysteries was born. The wow signal, as it came to be known, represented everything that SETI researchers had been hoping to find. It was strong, it was narrow, it came from the protected radio spectrum reserved for astronomical research, and it originated from a region of sky that seemed to hold no obvious natural radio source. What made the signal even more remarkable was its apparent motion across the sky. As the Earth rotated, the Big Ear's beam swept across the heavens, and the WOW signal rose and fell in intensity in exactly the pattern you would expect from a distant point source. It wasn't interference from a satellite or an airplane. It wasn't a glitch in the equipment. It behaved like something far away, something beyond our solar system, something that was calling out from the cosmic deep. The frequency of the signal held another clue. At 1420 megahertz, it was slightly blue shifted, meaning it appeared to be moving toward Earth at about 10 kilometers per second. This Doppler shift suggested that whatever was emitting the signal was approaching our solar system, though at a relatively modest pace compared to the high-speed encounters typical of astronomical objects. For nearly 5 decades, the WOW signal has remained one of the most compelling pieces of evidence in the search for extraterrestrial intelligence. Attempts to detect it again have failed. Follow-up observations of the same region of sky have found nothing unusual. The signal appeared once, blazed brilliantly for just over a minute, and then vanished into the cosmic silence, leaving behind only a handful of printed characters and an enduring mystery. But what if the answer to this mystery has been traveling toward us all along, hidden in the darkness of interstellar space, waiting for the right moment to reveal itself? What if the source of that famous signal wasn't a distant civilization broadcasting from some far-off star system, but something much closer, something that has been making its way toward our solar system for thousands of years? This is where our story takes an unexpected turn, leading us to the summer of 2025 and the discovery of an object that would challenge our understanding of both interstellar visitors and cosmic coincidences. On July 1st of that year, the Asteroid Terrestrial Impact Last Alert System, known as ATLAS, detected something extraordinary approaching from the depths of space. At first glance, it appeared to be another comet, trailing the characteristic tail of gas and dust that marks these ancient wanderers. But as astronomers studied its trajectory and composition, they realized they were looking at something far more remarkable. This wasn't just any comet. This was an interstellar visitor, only the third such object ever confirmed to be passing through our solar system from the space between the stars. The object, designated 3I/ATLAS, was remarkable in many ways. Its composition was unlike any comet from our solar system, with an unusually high ratio of carbon dioxide to water ice. Its nucleus was massive, estimated to be at least 5 kilometers across and weighing some 33 billion tons. It was traveling at an incredible speed of 58 kilometers per second relative to the Sun, far too fast to be captured by our star's gravity. But perhaps most intriguing of all was the direction from which 3I/ATLAS was approaching. As astronomers traced its trajectory backward through space, they found that this cosmic wanderer was arriving from the constellation Sagittarius, the same region of sky from which the WOW signal had originated nearly half a century earlier. This cosmic coincidence caught the attention of Harvard astrophysicist Avi Loeb, a scientist known for his willingness to consider unconventional explanations for astronomical phenomena. Loeb began to wonder whether there might be more than mere chance connecting these two mysterious events separated by decades of time and vast distances of space. Using precise orbital calculations, Loeb traced 3I/ATLAS backward through its journey across the galaxy. On August 12, 1977, just 3 days before the WOW signal was detected on Earth, the comet would have been positioned at coordinates in the sky that placed it remarkably close to the apparent source of that famous radio transmission. The angular separation between the two positions was only about 8 degrees, a coincidence that occurs by chance less than 1% of the time. The implications of this alignment are as fascinating as they are speculative. Could it be that the WOW signal originated not from a distant star system, but from this interstellar visitor as it approached our cosmic neighborhood? The power requirements for such a signal would be substantial, equivalent to the output of a nuclear reactor, but not beyond the realm of possibility for a sufficiently advanced technology. The signal's blue shift, indicating motion toward Earth, would align perfectly with 3I/ATLAS's approach velocity. The frequency choice of 1420 MHz, while significant for its connection to hydrogen, would also be an obvious choice for any civilization wanting to announce its presence to other technological species. And the transient nature of the signal, appearing once and never again, would make perfect sense if it originated from an object that was simply passing through our solar system on a one-time trajectory. Of course, the idea that 3I/ATLAS might be more than just a natural comet ventures into the realm of speculation. There is no direct evidence to suggest that this interstellar visitor is anything other than a perfectly natural chunk of ice and rock that happened to form in some distant star system billions of years ago. Its unusual composition could simply reflect the different conditions that existed in its stellar nursery compared to our own solar system. Yet as we drift into the realm of possibility, it's worth considering what we might expect from an interstellar probe designed to traverse the vast distances between star systems. Such a craft would need to be massive and durable to survive the journey through the hostile environment of interstellar space. It would likely be moving at tremendous speed to minimize travel time. And if it were designed to announce its presence to any civilizations it encountered along the way, what better signal to broadcast than one tuned to the universe's most fundamental frequency? The story of 3I/ATLAS is still being written as astronomers continue to study this remarkable visitor. Its closest approach to the Sun will occur in late October 2025, when it will pass within about 1.4 astronomical units of our star, just inside the orbit of Mars. This close encounter will provide researchers with their best opportunity to study the object's composition, structure, and behavior in detail. Already, observations from the James Webb Space Telescope have revealed that 3I/ATLAS is actively outgassing, creating a coma of gas and dust around its nucleus. This activity, driven by the sublimation of ices as the comet approaches the Sun, is producing a spectacular display visible to telescopes around the world. But it also raises questions about what might be hidden within that cloud of material. The gentle dance of ice and starlight around 3I/ATLAS tells us something profound about the nature of interstellar travel. As this cosmic wanderer approaches the warmth of our Sun, its ancient ices begin to stir, releasing gases that have been frozen in place for eons. This outgassing creates a magnificent tail that streams behind the comet like a banner, announcing its arrival from the depths of space. But within this beautiful display lies a puzzle that has captured the imagination of astronomers worldwide. The composition of these escaping gases is unlike anything we've seen in comets born within our solar system. The ratio of carbon dioxide to water vapor is extraordinarily high, suggesting that 3I/ATLAS formed in conditions very different from those that shaped our familiar celestial neighbors. This unusual chemistry has led some researchers to wonder whether we're looking at the remnants of a stellar system with a very different history than our own. Perhaps 3I/ATLAS originated around a star that was richer in heavy elements, or in a region of space where the processes of planetary formation unfolded in ways we're only beginning to understand. The comet's trajectory also tells a remarkable story. Tracing its path backward through the galaxy reveals a journey that has lasted millions, perhaps billions of years. This is no recent escape from a nearby star system, but rather an ancient wanderer that has been crossing the vast emptiness between stars for longer than complex life has existed on Earth. During its journey, it has witnessed the birth and death of stars, the formation of new planetary systems, and the slow evolution of the galaxy itself. As we contemplate this cosmic timeline, it's worth pausing to consider the profound loneliness of such a journey. For countless millennia, 3I/ATLAS has traveled through the near-perfect vacuum of interstellar space, surrounded by nothing but the faint glow of distant stars and the cosmic microwave background radiation that fills the universe. It has experienced temperatures barely above absolute zero, bombarded only by the occasional cosmic ray or grain of interstellar dust. Yet now, as it enters the inner regions of our solar system, this ancient traveller finds itself bathed in the warmth and light of a new star. The sun's radiation is awakening processes that have been dormant for geological ages, causing the comet to bloom like a flower in the cosmic spring. It's a transformation that speaks to the fundamental forces that shape matter throughout the universe, the eternal dance between heat and cold, light and darkness, motion and rest. The timing of 3I/ATLAS's arrival in our cosmic neighborhood raises intriguing questions about the nature of interstellar visitors. This is only the third such object we've definitively identified, following the mysterious Oumuamua in 2017 and Comet 2I/Borisov in 2019. Each of these visitors has brought its own mysteries and surprises, challenging our understanding of what exists in the space between stars. The rarity of these detections has led some astronomers to speculate that interstellar objects might be far more common than we realize, but that most pass through our solar system unnoticed. They move quickly and often along trajectories that don't bring them close enough to the sun to develop the bright tails that make comets easy to spot. How many cosmic wanderers have slipped past us in the darkness, their presence known only to the mathematical equations that govern orbital mechanics? The detection of 3I/ATLAS also represents a triumph of modern astronomical technology. The Atlas system that discovered it represents a new generation of sky surveys designed to continuously monitor the heavens for potentially hazardous asteroids and comets. These automated sentinels scan the sky night after night, comparing images to detect any object that moves against the background of stars. The fact that such systems are now sensitive enough to detect interstellar visitors opens up exciting possibilities for the future of astronomy. As our survey capabilities continue to improve, we may find that the space between stars is populated by a vast diaspora of objects ejected from their birth systems and now wandering the galaxy. Each one could tell us something unique about the conditions that existed when and where it formed. But returning to our central mystery, the potential connection between 3I/ATLAS and the WOW signal raises profound questions about how we search for evidence of intelligence in the universe. For nearly half a century, SETI researchers have focused primarily on detecting radio signals from distant star systems, assuming that any communication would originate from civilizations based on planets orbiting other stars. Yet, what if intelligence in the universe is more nomadic than we imagine? What if advanced civilizations have learned to build vessels capable of traversing interstellar distances, carrying their messages across the galaxy like bottles cast into a cosmic ocean? Such a strategy would have certain advantages over stationary broadcast stations. A mobile transmitter could visit multiple star systems, increasing the chances of making contact with other intelligent species. The power requirements for broadcasting a signal like the WOW signal from the distance of 3I/ATLAS in 1977 would indeed be substantial. Calculations suggest it would require energy output equivalent to a large nuclear reactor, a significant but not impossible engineering challenge for a sufficiently advanced civilization. The narrow bandwidth and precise frequency choice would indicate sophisticated radio technology, while the brief duration of the transmission could simply reflect the limited time available as the object passed through the optimal broadcasting position. The blue shift detected in the WOW signal, indicating motion toward Earth at about 10 kilometers per second, aligns intriguingly with what we might expect from 3I/A TLAS during its approach to our solar system. This Doppler shift has long puzzled researchers. As it suggested, the source was moving in a way that didn't match any known astronomical object in that region of sky. Of course, we must acknowledge that correlation does not imply causation. The alignment between these two phenomena could indeed be nothing more than an extraordinary coincidence. The universe is vast and filled with countless objects and events, making it statistically inevitable that some seemingly meaningful coincidences will occur purely by chance. Modern astronomical research has also provided alternative explanations for the WOW signal that don't require extraterrestrial intelligence. Recent studies have suggested that the signal might have originated from a natural astrophysical process involving hydrogen clouds in interstellar space. These clouds, when excited by powerful radiation from sources like magnetars or flaring stars, can produce intense radio emissions at the characteristic hydrogen frequency. Such events would be extremely rare and transient, explaining why the WOW signal was never detected again despite numerous follow-up observations. The theory proposes that a brief but intense burst of radiation from a distant astronomical object passed through a cloud of neutral hydrogen, causing it to emit a powerful radio signal that was detected by the Big Ear telescope. This explanation has the advantage of relying on known physics and observed astronomical phenomena. Magnetars, neutron stars, with magnetic fields trillions of times stronger than Earth's, are known to produce sudden, powerful bursts of radiation that can be detected across vast distances. While these exotic objects weren't discovered until after 1977, we now know they exist throughout the galaxy and occasionally produce the kind of energetic outbursts that could trigger the proposed mechanism. The interstellar medium, the thin gas and dust that fills the space between stars, contains vast quantities of neutral hydrogen. These diffuse clouds are normally invisible at radio wavelengths, but they can be excited to emit radiation when subjected to intense external energy sources. The process would produce a signal with exactly the characteristics observed in the WOW signal: narrow bandwidth, high intensity, and emission at the hydrogen frequency. Yet even as we consider these natural explanations, the mystery of 3I/ATLAS continues to unfold. As this interstellar visitor approaches its closest point to the Sun, astronomers around the world are training their instruments on it, hoping to unlock its secrets. Every spectrum analyzed, every image captured, adds to our understanding of this remarkable object and the stellar system from which it originated. The comet's unusual orbital characteristics continue to intrigue researchers. Its trajectory is nearly perfectly aligned with the plane of our solar system, a configuration that occurs by chance in fewer than 1 in 500 cases for randomly oriented interstellar objects. This alignment, combined with its retrograde motion traveling opposite to the direction of planetary orbits, creates a unique dynamical signature that sets it apart from other known interstellar visitors. As 3I/ATLAS continues its journey through our solar system, it carries with it the accumulated story of its origins. Locked within its icy nucleus are chemical signatures that could tell us about the composition of its birth cloud, the nature of its parent star, and the processes that ejected it into interstellar space. These are stories written in the language of atoms and molecules, waiting to be decoded by spectroscopic analysis. The study of interstellar objects like 3I/ATLAS represents a new frontier in astronomy, offering us direct samples of material from other stellar systems without the need for interstellar travel. Each visitor brings unique information about conditions elsewhere in the galaxy, expanding our understanding of planetary formation and stellar evolution beyond the confines of our own cosmic neighborhood. The gentle dance between speculation and scientific rigor continues as we consider what 3I/ATLAS might reveal about the nature of cosmic wanderers. As this ancient traveler makes its way through the inner solar system, it offers us a rare opportunity to study material that has journeyed between the stars for millions of years. Each photon of light reflected from its surface, each molecule in its glowing tail, carries information about distant realms we may never visit. The timing of its arrival in our cosmic neighborhood raises fascinating questions about the rhythm of interstellar migration. How often do such visitors pass through our solar system undetected? Are we witnessing a relatively common phenomenon that has simply escaped our notice until recent advances in astronomical surveillance? Or is 3I/ATLAS part of a rare class of objects that venture into the gravitational embrace of foreign stars? The answer may lie in the subtle patterns of its approach. Unlike the familiar comets that call our solar system home, 3I/ATLAS follows a trajectory that speaks of origins in the deep galactic wilderness. Its path carries it not from the distant Oort cloud that surrounds our sun, but from the vast emptiness between star systems, where temperatures hover just above absolute zero and matter is spread so thin that a handful of atoms might occupy a volume the size of a cathedral. This interstellar environment is profoundly different from the relatively cozy confines of our solar system. Out there, beyond the reach of our sun's warming influence, space is dominated by the faint glow of distant stars and the cosmic microwave background radiation left over from the Big Bang itself. It's a realm where time moves differently, where change occurs on scales measured not in years or centuries, but in millions or billions of years. For 3I/ATLAS to have survived such a journey intact suggests it possesses remarkable durability. The interstellar medium, while incredibly sparse, is not entirely empty. Cosmic rays, high-energy particles accelerated by stellar explosions and magnetic fields, constantly bombard any object traveling through this space. Over millions of years, this radiation can alter the surface chemistry of astronomical bodies, creating new compounds and breaking down existing ones. The fact that 3I/ATLAS still retains its distinctive chemical signature tells us something important about either its composition or the protective mechanisms that have shielded it during its long journey. Perhaps its unusual abundance of carbon dioxide ice provided a kind of natural armor, sublimating away slowly under cosmic ray bombardment while protecting the more volatile compounds beneath. As we contemplate these cosmic scales of time and distance, it's worth pausing to consider the profound patience required for interstellar travel. Any civilization advanced enough to send messages or probes between star systems would need to think in terms of geological ages rather than human lifespans. The nearest star to our sun is over 4 light-years away, meaning that even at the tremendous speeds achieved by 3I/ATLAS, such a journey would require tens of thousands of years. This temporal gulf presents both challenges and opportunities for any hypothetical interstellar communication. On one hand, the vast timescales involved make traditional back-and-forth conversation impossible. A signal sent to a nearby star system today wouldn't receive a reply for nearly a decade, and that assumes someone is listening and chooses to respond immediately. On the other hand, these same vast timescales might favor a different kind of communication strategy. Instead of trying to establish real-time dialogue across interstellar distances, an advanced civilization might choose to send self-contained messages that could function independently over long periods. Think of them as cosmic time capsules designed to operate autonomously as they traverse the galaxy. Such messages might take the form of physical objects rather than ephemeral radio signals. A probe or artifact could carry vast amounts of information encoded in its structure, its materials, even its trajectory through space. Unlike a radio transmission that fades with distance and disappears forever once it passes, A physical message could persist for millions of years, waiting patiently for the right moment to reveal its contents. The technology required for such an approach would be substantial, but not necessarily beyond the reach of a sufficiently advanced civilization. Creating objects capable of surviving interstellar travel would require mastery of materials, science, propulsion systems, and perhaps most importantly, information storage and retrieval systems that could function reliably over cosmic timescales. In this context, the unusual characteristics of 3I/ATLAS take on new significance. Its massive size, unusual composition, and precisely calculated trajectory could all be features of deliberate design rather than natural coincidence. The object's approach from Sagittarius, the same region associated with the wow signal, adds another layer of intrigue to this cosmic puzzle. Of course, we must remember that extraordinary claims require extraordinary evidence, and the scientific method demands that we consider the most mundane explanations before entertaining more exotic possibilities. The properties that make 3I/ATLAS unusual could all result from perfectly natural processes operating in stellar environments very different from our own. The high carbon dioxide content, for instance, might simply reflect the composition of the molecular cloud from which it formed. Different regions of the galaxy have different chemical abundances, depending on their stellar formation history and the elements produced by previous generations of stars. A comet forming in a region rich in carbon-bearing molecules might naturally develop the composition we observe in 3I/ATLAS. Similarly, the object's trajectory and timing could result from the complex gravitational choreography of galactic dynamics. Stars and their planetary systems don't remain fixed in space, but orbit the galactic center in great sweeping arcs that take hundreds of millions of years to complete. The ejection of objects from one stellar system and their eventual encounter with another is an inevitable consequence of this cosmic dance. Recent advances in our understanding of planetary formation have revealed that the early stages of stellar system development are incredibly violent and chaotic. Young stars are surrounded by turbulent disks of gas and dust from which planets slowly condense. During this process, gravitational interactions can fling countless objects into interstellar space, creating a vast population of cosmic refugees wandering between the stars. Computer simulations suggest that our own solar system likely ejected far more material than it retained during its formation 4.5 billion years ago. If this pattern holds throughout the galaxy, then interstellar space should be filled with objects like 3I/ATLAS, remnants of planetary formation processes that occurred around countless other stars. The challenge lies in detecting these wanderers. Most interstellar objects would be dark and cold, invisible against the black backdrop of space, until they happen to pass close enough to a star to begin outgassing and developing the bright tails that make them detectable. The 3 interstellar visitors we've identified so far might represent just the tip of an enormous iceberg. This possibility has profound implications for our understanding of the galaxy's structure and history. If interstellar objects are as common as some models suggest, they represent a vast reservoir of material that has been mixing and redistributing throughout the galaxy for billions of years. Each object carries with it chemical and isotopic signatures from its birth environment, creating a kind of archaeological record of stellar formation and evolution. The study of these cosmic wanderers might eventually allow us to reconstruct the chemical history of different regions of the galaxy, tracking how elements produced by stellar nucleosynthesis have spread through space over cosmic time. It's a detective story written in atomic signatures, with each interstellar visitor providing new clues about the galaxy's past. But returning to our central mystery, the potential connection between 3I/ATLAS and the wow signal continues to capture the imagination of researchers and the public alike. Even if this connection proves to be nothing more than an intriguing coincidence, it highlights the importance of keeping an open mind when confronting the unknown. The history of science is filled with discoveries that initially seemed impossible or absurd, but later proved to be fundamental to our understanding of the natural world. Continental drift was ridiculed when first proposed, but is now understood to be driven by plate tectonics. The idea that bacteria could cause stomach ulcers was initially dismissed, but earned its discoverers a Nobel Prize. In the realm of astrobiology and SETI research, we must balance healthy skepticism with intellectual curiosity. The universe is under no obligation to conform to our expectations or prejudices. Life, if it exists elsewhere, might have evolved along pathways we haven't imagined. Intelligence, if it has arisen in other stellar systems, might express itself in ways we haven't anticipated. The search for extraterrestrial intelligence has traditionally focused on radio signals, because that's the technology we understand best. But an advanced civilization might have moved beyond radio communication entirely, using techniques based on principles we haven't discovered, or technologies we can't yet imagine. Perhaps they encode information in the quantum states of particles, or modulate gravitational waves, or embed messages in the genetic codes of extremophile organisms designed to survive interstellar travel. The possibilities are limited only by the laws of physics and the creativity of minds that might think very differently from our own. This is why objects like 3I/ATLAS deserve careful study regardless of their origin. Whether they represent natural phenomena or something more exotic, they expand our knowledge of what's possible in the universe. Each measurement, each analysis, each observation adds to the growing body of data that will eventually help us understand our place in the cosmic order. The gentle passage of 3I/ATLAS through our solar system serves as a reminder of the vast scales on which cosmic processes operate. While we measure our lives in decades and our civilizations in centuries or millennia, the universe operates on timescales that dwarf human experience. Stars are born, live, and die over billions of years. Galaxies collide and merge over even longer periods. The cosmic microwave background radiation we detect today began its journey when the universe was less than 400,000 years old. In this context, the 48 years that separate the wow signal from the discovery of 3I/ATLAS represent barely an instant. If these two events are indeed connected, they remind us that cosmic phenomena often unfold over timescales that span human generations. What appears to us as separate, isolated events might actually be part of larger patterns that become apparent only when viewed from the proper temporal perspective. The continuing journey of 3I/ATLAS through our solar system offers a unique opportunity to test our theories about interstellar objects and their properties. As it approaches its closest point to the Sun in late October 2025, the increasing solar radiation will drive more vigorous outgassing, potentially revealing new details about its internal composition and structure. Ground-based telescopes and space-based observatories around the world are already training their instruments on this cosmic visitor, capturing spectra that reveal the molecular fingerprints of the gases streaming from its nucleus. Each observation adds another piece to the puzzle, helping us understand not just 3I/ATLAS itself, but the broader population of interstellar objects that it represents. The data gathered during this encounter will inform our search for future interstellar visitors and help us develop better techniques for detecting and studying them. As our survey capabilities continue to improve, we may find that such objects are far more common than we currently realize, opening up new avenues for studying the chemical and physical processes that operate throughout the galaxy. Whether 3I/ATLAS proves to be a natural comet from a distant star system or something more extraordinary, its passage through our cosmic neighborhood represents a moment of connection across the vast emptiness of space. For a brief time, this ancient wanderer shares our small corner of the galaxy, offering us a glimpse into realms we may never visit in person. As we drift toward the conclusion of our gentle exploration, it's worth reflecting on what these cosmic mysteries teach us about the nature of discovery itself. The universe is vast beyond imagining, filled with phenomena that challenge our understanding and objects that defy our expectations. Each new discovery, whether it confirms our theories or overturns them, adds to the grand tapestry of human knowledge. The WOW signal and 3I/ATLAS, whether connected or coincidental, remind us that the cosmos still holds secrets waiting to be uncovered. They encourage us to keep listening, keep watching, keep wondering about what might be out there in the darkness between the stars. In a universe filled with billions of galaxies, each containing billions of stars, the possibilities are as limitless as the night sky itself. As we settle deeper into this cosmic meditation, let's explore what makes these interstellar encounters so profoundly moving to contemplate. There's something almost poetic about the way 3I/ATLAS has timed its arrival in our solar system, as if the universe itself were orchestrating a grand revelation across the centuries. The mathematics of celestial mechanics tell us that this visitor has been approaching our sun for millions of years, following a trajectory carved by the subtle gravitational influences of countless stars. During its journey through the galactic wilderness, civilizations have risen and fallen on Earth. Species have evolved and vanished, and the very continents have shifted their positions. Yet through all this terrestrial change, 3I/ATLAS has maintained its steady course toward this moment of cosmic convergence. When we consider the delicate choreography required for such an encounter, the precision becomes almost breathtaking. The comet's path had to be influenced by just the right stellar gravitational fields, deflected by precisely the correct amount, and timed to arrive at our solar system during the brief window when humanity possessed the technology to detect and study it. A few thousand years earlier or later, and it would have passed unnoticed through our cosmic neighborhood, its secrets remaining forever hidden. This timing raises fascinating questions about the nature of observation and discovery in astronomy. How many cosmic messengers have visited our solar system throughout Earth's history, carrying information from distant stellar nurseries, only to depart unseen because no eyes were watching? The dinosaurs witnessed meteor showers and cometary displays that we can only imagine, while our ancestors looked up at night skies filled with phenomena that remain invisible to our modern, light-polluted observations. The story of 3I/ATLAS also speaks to the remarkable patience required for cosmic investigations. Unlike laboratory experiments that can be repeated at will, astronomical phenomena often present themselves once and then vanish forever. The brief passage of an interstellar visitor represents a fleeting opportunity that may not come again for millions of years. Consider the dedication of the astronomers who have spent decades scanning the skies for exactly such objects. Night after night, they point their telescopes toward the darkness, knowing that most observations will reveal nothing unusual. Yet they persist, driven by the understanding that each empty field of view brings them statistically closer to the next great discovery. The Atlas survey system that discovered our cosmic visitor represents the culmination of this patient methodology. Automated telescopes now conduct this vigil for us, comparing millions of images each night, searching for the telltale motion that betrays an object moving against the background of distant stars. It's a kind of mechanical meditation, a technological prayer offered to the universe in the hope of revelation. When such revelations do occur, they often arrive with a cascade of new questions that expand our understanding in unexpected directions. The unusual composition of 3I/ATLAS, with its remarkably high ratio of carbon dioxide to water ice, challenges our models of how comets form and evolve. This chemical signature suggests formation conditions unlike anything we observe in our own solar system, opening windows into stellar environments we can study in no other way. The implications extend far beyond a single comet. If 3I/A TLAS formed around a star with different metallicity than our Sun, its composition provides direct evidence of nucleosynthetic processes operating in distant stellar environments. The elements locked within its nucleus were forged in the nuclear furnaces of stars that lived and died before our solar system even existed. Their ashes scattered into space to eventually coalesce into the object we now observe. This cosmic recycling represents one of the most beautiful aspects of stellar astronomy. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were created inside massive stars that exhausted their nuclear fuel billions of years ago. When those ancient suns exploded as supernovae, they scattered these heavy elements into space, where they became incorporated into new generations of stars, planets, and eventually, life itself. 3I/A TLAS carries within its frozen nucleus a different chapter of this ongoing story. Its exotic chemistry tells of stellar environments where different ratios of elements were available during planetary formation, where the balance between carbon, oxygen, nitrogen, and other crucial building blocks followed pathways unknown in our cosmic vicinity. The study of such variations has profound implications for astrobiology and our understanding of where life might arise in the universe. If planetary formation processes can produce such dramatically different chemical environments, then the conditions suitable for life might be far more diverse than we currently imagine. What seems exotic and inhospitable to us might represent perfectly normal conditions in other regions of the galaxy. As 3I/A TLAS continues its approach toward perihelion, its increasing activity provides a real-time laboratory for studying these alien chemistry sets. The gases streaming from its nucleus create spectral lines that serve as fingerprints, revealing not just what elements are present, but in what proportions and molecular forms. Each spectrum captured by our telescopes adds another data point to our growing understanding of interstellar chemistry. The comet's behavior as it approaches the Sun also offers insights into the physical processes that govern cometary activity. The way its coma develops, the rate at which it loses mass, and the patterns in its gas production all provide clues about its internal structure and composition. These observations help us understand not just 3I/A TLAS itself, but the broader population of interstellar objects that it represents. Modern spectroscopic techniques allow astronomers to identify specific molecules in the comet's tail with remarkable precision. Water vapor, carbon monoxide, carbon dioxide, methane, ammonia, and dozens of other compounds can be detected and measured, creating a detailed inventory of the materials that formed in some distant stellar nursery billions of years ago. But beyond the scientific data lies something more profound, a sense of connection across the vast emptiness of space. When we observe 3I/A TLAS through our telescopes, we're engaging in a form of cosmic archaeology, studying artifacts from stellar systems we may never visit. Each photon of light that reaches our detectors has traveled alongside this ancient wanderer for part of its interstellar journey, carrying information across distances that challenge human comprehension. The gentle glow surrounding 3I/A TLAS as it awakens in our Sun's warmth represents a kind of stellar rebirth. Materials that have been frozen for millions of years are stirring back to life, sublimating from solid ice directly into gas, creating the beautiful coma and tail that make the comet visible to our instruments. It's a process that transforms a dark, invisible object into a brilliant beacon, announcing its presence to anyone with eyes to see. This transformation reminds us of the dynamic nature of our universe, where even the apparently eternal dance of stars and planets is constantly changing on timescales beyond human experience. What appears stable and unchanging to us is actually part of a vast, slow-motion choreography of matter and energy that has been unfolding since the universe began. The detection of 3 interstellar objects in less than a decade suggests that such visitors may be far more common than we previously realized. Our improving survey capabilities are revealing a population of cosmic wanderers that has always been there, moving through the darkness between stars, occasionally passing close enough to our own star to become visible in our telescopes. Each of these visitors tells a unique story. Oumuamua, the first confirmed interstellar object, puzzled astronomers with its unusual, elongated shape and unexpected acceleration as it departed our solar system. Comet 2. I/Borisov appeared more familiar, behaving much like comets from our own Oort cloud despite its exotic origin. Now 3 I/ATLAS brings its own mysteries, challenging our understanding once again with its unusual chemistry and intriguing timing. The diversity among these 3 objects hints at the incredible variety that might exist in the interstellar population. If each stellar system ejects objects during its formation process, then the space between stars could be filled with samples from millions of different cosmic environments, each carrying its own unique chemical signature and formation history. The implications for astrobiology are particularly intriguing. If interstellar objects regularly carry organic molecules between star systems, they could serve as vehicles for distributing the chemical building blocks of life throughout the galaxy. Complex organic compounds detected in meteorites and comets from our own solar system demonstrate that the chemistry of life can operate in the harsh environment of space. Could interstellar visitors like 3 I/ATLAS be carrying similar organic cargo from their distant birthplaces? The answer may come from detailed spectroscopic analysis of the comet's outgassing products as it approaches the Sun. If complex organic molecules are detected in its coma, it would provide direct evidence that the chemistry of life operates in stellar environments very different from our own. This possibility connects to broader questions about the distribution of life in the universe. Rather than being confined to individual planetary systems, life's chemical precursors might be constantly mixing and redistributing throughout the galaxy via interstellar objects. What we think of as separate, isolated stellar systems might actually be part of a vast network of chemical exchange operating over cosmic timescales. The concept challenges our traditional thinking about the search for extraterrestrial life. Instead of looking only for radio signals or atmospheric biosignatures from distant planets, we might also search for evidence of biological processes in the interstellar objects that regularly visit our solar system. Such visitors could carry direct samples of life or its chemical precursors from other stellar environments. Of course, the detection of organic molecules in interstellar objects wouldn't necessarily indicate the presence of life in their birth systems. Complex organic chemistry can occur through purely abiotic processes, and many of the organic compounds found in meteorites and comets can be produced without biological intervention. But such discoveries would still represent important steps toward understanding the chemical conditions that might support life elsewhere in the galaxy. The gentle passage of 3 I/ATLAS through our solar system offers a unique window into these possibilities. As one of only 3 confirmed interstellar visitors, it represents an incredibly rare opportunity to study material from another stellar system without the need for interstellar travel. Every spectrum captured, every image recorded, adds to our understanding of the cosmic processes that shape matter throughout the galaxy. The timing of its arrival, nearly half a century after the WOW signal, adds another layer of intrigue to this cosmic story. Whether this temporal coincidence represents something meaningful or merely the random alignment of unrelated events, it serves as a reminder of how much we still don't know about our universe and our place within it. As we contemplate these mysteries in the gentle darkness of night, there's something deeply comforting about the steady progression of cosmic events. While human affairs often seem chaotic and unpredictable, the universe operates according to physical laws that we can understand and predict with remarkable precision. The trajectory of 3 I/ATLAS was determined millions of years ago by the gravitational influences it encountered during stellar journey, yet we its inter can calculate its future path with extraordinary accuracy. This predictability provides a kind of cosmic anchor in an uncertain world. Whatever challenges we face as a species, whatever changes occur in our technology and society, the stars will continue their ancient dance according to the same physical principles that have governed them for billions of years. There's something profoundly reassuring about this continuity, a reminder that we're part of something much larger and more enduring than our immediate concerns. The story of 3 I/ATLAS and its potential connection to the WOW signal illustrates the importance of maintaining both scientific rigor and open-minded curiosity when confronting cosmic mysteries. While we must be careful not to let our imaginations run ahead of the evidence, we must also remain open to possibilities that might initially seem unlikely or unconventional. The universe has surprised us repeatedly throughout the history of astronomy. Black holes, neutron stars, dark matter, dark energy, exoplanets, and countless other phenomena were once considered exotic theoretical possibilities before becoming accepted parts of our cosmic worldview. Each discovery has expanded our understanding of what's possible in the universe, often in ways we couldn't have anticipated. As 3 I/ATLAS continues its journey through our solar system, it carries with it the potential for new discoveries that might once again challenge our assumptions about the cosmos. Whether it proves to be a perfectly ordinary interstellar comet or something more extraordinary, its study will contribute to our growing understanding of the galaxy beyond our solar system. The gentle rhythm of scientific discovery continues, driven by the patient accumulation of observations and measurements that gradually reveal the universe's secrets. Each night, telescopes around the world point toward the darkness, collecting photons that have traveled across vast distances to reach our detectors. Each spectrum analyzed, each orbit calculated, each chemical signature decoded, adds another piece to the grand puzzle of cosmic understanding. In this ongoing quest for knowledge, objects like 3 I/ATLAS serve as ambassadors from the depths of space, carrying information from realms we may never visit in person. They remind us that we live in a universe filled with wonders beyond our current comprehension, where the next great discovery might be approaching even now through the darkness between the stars. As we drift towards sleep, contemplating these cosmic mysteries, we can take comfort in knowing that the universe continues its patient work of revelation. Somewhere in the night sky, ancient light is beginning new journeys that will take millions of years to complete. Somewhere in the depths of space, new worlds are forming around young stars, while others complete their final chapters in spectacular supernovae that scatter the elements of future life across the galaxy. The story of 3 I/ATLAS and the enduring mystery of the WOW signal remind us that we're living through a remarkable moment in human history, when our technology has finally become sophisticated enough to detect and study visitors from other star systems. We stand at the threshold of a new era of discovery, where each interstellar object that passes through our cosmic neighborhood offers fresh insights into the nature of the galaxy and our place within it. Whether this cosmic coincidence represents something profound or merely the statistical inevitability of rare events occurring in an infinite universe, it invites us to consider how discovery itself unfolds across time. The astronomers who first detected the WOW signal had no way of knowing that decades later, an object would be discovered approaching from the same region of sky. Similarly, those studying 3 I/ATLAS today cannot predict what connections future discoveries might reveal. This uncertainty is perhaps one of the most beautiful aspects of scientific inquiry. We build our understanding piece by piece observation by observation, never quite knowing when the next measurement might transform our entire perspective. The universe seems to delight in presenting us with puzzles that require decades or centuries to solve, if indeed they can be solved at all. The study of 3I/ATLAS has already begun to reveal details that distinguish it from any object born within our solar system. Its retrograde orbit, travelling opposite to the direction of planetary motion, marks it as a clear outsider. This backward dance through our cosmic neighbourhood creates a kind of celestial counterpoint, as if the universe were playing a melody in reverse. The comet's nearly perfect alignment with the plane of our solar system represents another statistical rarity. Most objects approaching from interstellar space would be expected to arrive at random angles, reflecting the chaotic nature of galactic dynamics. Yet 3I/ATLAS follows a path that seems almost deliberately chosen to maximize its visibility from Earth. These orbital characteristics have prompted some researchers to wonder whether we're witnessing pure chance or something more intentional. The mathematical precision required for such an alignment suggests either extraordinary luck or extraordinary planning. While natural processes can certainly produce surprising coincidences, the accumulation of unusual features in a single object inevitably raises questions. The comet's massive size adds another layer to this puzzle. At over 5 kilometers in diameter and weighing tens of billions of tons, 3I/ATLAS represents a substantial chunk of material that somehow survived ejection from its birth system and the long journey through interstellar space. Most objects torn from their stellar nurseries would be much smaller, fragments rather than substantial bodies. The survival of such a large object through millions of years of interstellar travel suggests either remarkable durability or protection from some source. The harsh environment between stars subjects traveling objects to constant bombardment from cosmic rays, micrometeoroids, and the subtle but persistent pressure of starlight itself. Over cosmic timescales, these influences can erode even substantial bodies down to dust. Yet 3I/ATLAS appears to have maintained its structural integrity throughout its journey, arriving in our solar system with enough volatile materials to produce the spectacular outgassing display we observe today. This preservation of ancient ices speaks to either an unusually protective composition or perhaps a more recent origin than its trajectory might suggest. The chemical analysis of the comet's emissions continues to yield surprises. The unusual abundance of carbon dioxide relative to water ice creates spectral signatures unlike anything observed in objects from our solar system's outer reaches. This exotic chemistry provides a direct window into conditions that existed around a distant star billions of years ago. Each molecule detected in 3I/ATLAS's coma represents a fossil from another world, preserved in the deep freeze of interstellar space and now awakening in the warmth of our sun. These chemical messengers carry information about stellar nuclear synthesis processes, planetary formation conditions, and perhaps even the potential for life in environments very different from our own. The isotopic ratios found within these molecules will prove particularly revealing. Different stellar environments produce characteristic signatures in the relative abundances of various atomic isotopes. By comparing these signatures with those found in solar system objects, astronomers can begin to reconstruct the type of star around which 3I/ATLAS likely formed. Was its parent star more massive than our Sun, burning brighter and hotter during its main sequence lifetime? Did it form in a region of the galaxy richer or poorer in heavy elements than our cosmic neighbourhood? These questions can be answered through careful analysis of the comet's chemical fingerprints, providing insights into stellar environments we may never observe directly. The timing of 3I/ATLAS's closest approach to the Sun in late October 2025 has created a sense of anticipation throughout the astronomical community. This perihelion passage represents the peak of observational opportunity, when solar heating will drive maximum outgassing and reveal the comet's inner secrets most clearly. Observatories around the world have coordinated observing campaigns to capture this cosmic event from multiple perspectives. Radio telescopes will search for any unusual emissions that might echo the famous signal from 1977. Optical telescopes will analyze the comet's spectrum in unprecedented detail. Space-based instruments will study its behavior free from atmospheric interference. This coordinated effort represents the best of international scientific collaboration, with researchers sharing data and insights across national boundaries in pursuit of understanding. The brief window of 3 I/ATLAS's passage demands such cooperation, as no single observatory can capture all the information this visitor might reveal. The psychological impact of studying an interstellar visitor extends beyond pure scientific curiosity. There's something profoundly moving about examining material that formed around another star, that has journeyed across the galaxy to reach our cosmic doorstep. Each observation connects us, however tenuously, to stellar systems we can barely imagine. This connection operates on multiple levels. Scientifically, 3I/ATLAS provides direct access to materials and conditions from distant stellar environments. Philosophically, it reminds us that our solar system is not isolated, but part of a vast galactic community where matter and energy flow between star systems over cosmic time. The comet's approach also highlights the dynamic nature of our galactic neighborhood. What we often think of as the stable, unchanging cosmos is actually in constant motion, with objects regularly exchanging between stellar systems. Our Sun and its planets travel through space at hundreds of kilometers per second, encountering new regions of the interstellar medium as we orbit the galactic center. This motion means that the view from Earth is constantly changing on timescales far longer than human civilization. The constellations we use to navigate our night sky represent a temporary arrangement of stars that will look completely different millions of years from now. In this context, the arrival of 3 I/ATLAS represents just one moment in an ongoing cosmic conversation between stellar systems. The potential connection to the WOW signal adds a layer of mystery that transcends pure astrophysics. If these events are indeed related, they suggest forms of cosmic communication or activity operating on timescales that dwarf human experience. A signal transmitted in 1977 and an object discovered in 2025 would represent coordination across nearly half a century of Earth time. Such temporal gaps challenge our assumptions about how intelligence might operate in the universe. We tend to think in terms of immediate cause and effect, expecting responses to occur within timeframes meaningful to human experience. But cosmic intelligence, if it exists, might operate according to very different temporal rhythms. Consider the patience required for interstellar communication using physical objects rather than electromagnetic signals. A civilization choosing to send information via comet or probe would be committing to a strategy spanning millions of years. The planners of such a mission would never live to see its completion, requiring a kind of species-level thinking that transcends individual lifespans. This perspective transforms our understanding of what cosmic communication might look like. Instead of expecting rapid exchanges of messages, we might need to search for patterns that unfold over geological timescales. The WOW signal and 3 I/ATLAS, separated by decades of time but potentially connected by origin, might represent just such a pattern. The blue shift detected in the original WOW signal continues to intrigue researchers studying this potential connection. The signal's apparent motion toward Earth at roughly 10 kilometers per second aligns remarkably well with what we might expect from 3 I/ATLAS during its approach to our solar system in 1977. This Doppler signature has long puzzled SETI researchers, as it suggested the signal source was moving in a way that didn't match any known astronomical object in the Sagittarius region. The discovery of 3 I/ATLAS approaching from the same direction provides, for the first time, a plausible explanation for this mysterious velocity component. The narrow bandwidth of the WOW signal also takes on new significance in light of modern understanding of natural radio sources. Most astrophysical phenomena that produce radio emissions do so across broad ranges of frequencies. The precision and focus of the 1977 signal suggested either highly unusual natural processes or artificial origin. Recent theoretical work on magnetar flares and hydrogen cloud interactions has provided natural mechanisms that could produce narrowband signals at the hydrogen frequency. These processes require precise alignments of astronomical objects and timing that would make them extremely rare events. The transient nature of such phenomena would explain why the WOW signal was never detected again, despite numerous follow-up observations. Yet even these natural explanations require remarkable coincidences to account for the signal's specific characteristics. The alignment of a magnetar, hydrogen cloud, and Earth's radio telescopes would need to occur with extraordinary precision to produce the observed signal strength and frequency stability. The addition of 3 I/ATLAS to this cosmic equation introduces yet another layer of coincidence. For a natural explanation to account for both the WOW signal and the interstellar visitor's trajectory, we must invoke a series of alignments and timing that stretch the bounds of statistical plausibility. This is where the scientific method proves its value in distinguishing between correlation and causation. The appearance of meaningful patterns in random data is a well-known psychological phenomenon that has led countless researchers astray throughout history. Our brains are exquisitely evolved to detect patterns and connections, even when none exist. The challenge lies in determining when apparent patterns reflect genuine physical relationships and when they represent the inevitable result of searching for meaning in vast datasets. With billions of astronomical objects and events to choose from, some coincidences are statistically inevitable. Yet the specific nature of the WOW signal and 3 I/ATLAS connection goes beyond simple coincidence. The angular alignment, temporal correlation, and velocity matching create a combination of factors that occurs by chance, less than once in several hundred similar cases. The scientific community's response to this potential connection reflects the careful balance between skepticism and open-mindedness that characterizes good research. Most astronomers remain cautious about drawing firm conclusions from correlational evidence, while acknowledging that the apparent connection deserves serious investigation. This measured approach serves science well, preventing premature acceptance of extraordinary claims while ensuring that genuinely revolutionary discoveries aren't dismissed out of hand. The history of astronomy is filled with observations that initially seemed impossible, but later proved to reveal fundamental truths about the universe. The detection of pulsars in 1967 initially seemed so artificial that researchers half-seriously considered the possibility of extraterrestrial signals before recognizing these objects as rapidly rotating neutron stars. The discovery of the cosmic microwave background radiation was initially attributed to pigeon droppings before being recognized as evidence for the Big Bang. More recently, the acceleration of the universe's expansion seemed so contrary to expectations that it took years of careful verification before being accepted as evidence for dark energy. Each of these discoveries reminds us that the universe often behaves in ways that challenge our preconceptions. The study of 3 I/ATLAS proceeds within this framework of cautious investigation and open-minded analysis. Every measurement is carefully calibrated, every conclusion tentatively held pending additional evidence. This methodical approach may seem slow and overly conservative, but it represents humanity's best strategy for distinguishing genuine discoveries from wishful thinking. As the comet continues its approach toward perihelion, the intensity of scientific scrutiny increases. Spectrographs dissect its light into component wavelengths, revealing the chemical signatures of molecules that formed in another stellar system. Photometers measure subtle changes in brightness that might indicate rotation or outgassing variations. Radio telescopes listen for any emissions that might echo across the decades to that famous August night in 1977. Each observation adds another data point to our growing understanding of this cosmic visitor. The accumulation of measurements gradually builds a picture of an object unlike any other we've studied, carrying within its ancient nucleus the frozen history of stellar processes that occurred billions of years ago. The international nature of this observational campaign reflects the global character of modern astronomy. Telescopes in Chile scan the southern sky, while observatories in Hawaii track the comet's northern passage. European and Asian facilities contribute their specialized instruments to the effort, creating a worldwide network of scientific surveillance. This coordination represents one of humanity's greatest achievements, the ability to work together across cultural and political boundaries in pursuit of knowledge. The brief passage of an interstellar visitor demands such cooperation, as no single nation or institution possesses all the tools needed to unlock its secrets. The data flowing from these observations will take months or years to fully analyze. Spectroscopic measurements require careful calibration and comparison with laboratory standards. Chemical abundances must be calculated from emission line strengths. Orbital dynamics need precise tracking over extended periods to determine the comet's exact trajectory. Yet even preliminary results have begun to confirm 3I/ATLAS's exotic nature. Its chemical composition continues to set it apart from solar system objects, while its physical behavior reveals processes shaped by interstellar environments. Each new measurement reinforces its status as a genuine visitor from another stellar realm. The broader implications of studying interstellar objects extend far beyond individual discoveries. These cosmic ambassadors provide our only direct access to materials from other star systems, offering insights into planetary formation processes operating throughout the galaxy. If interstellar objects prove to be as common as some models suggest, they represent a vast reservoir of information about stellar environments across space and time. Each visitor carries chemical signatures from its birth system, isotopic ratios that reveal stellar nucleosynthesis processes, and physical properties that reflect formation conditions. The systematic study of such objects could eventually allow us to map the chemical evolution of the galaxy, tracking how elements produced by stellar fusion and supernova explosions have spread through space over cosmic time. This galactic archaeology would reveal patterns of star formation and element distribution that shape the environments where planets and potentially life could develop. The implications for astrobiology are particularly profound. If organic molecules prove to be common in interstellar objects, it would suggest that the chemical building blocks of life are distributed throughout the galaxy. Complex organic chemistry might be occurring in interstellar space itself, driven by cosmic ray interactions and stellar radiation. Such discoveries would transform our understanding of life's potential distribution in the universe. Rather than being confined to planetary surfaces, the chemistry of life might be operating throughout the galaxy, creating a vast network of organic synthesis that connects distant stellar systems. The gentle passage of 3I/ATLAS through our solar system thus represents more than just an astronomical curiosity. It offers a window into processes that operate on galactic scales, connecting our local cosmic environment to the broader universe in ways we're only beginning to understand. As we contemplate these possibilities in the quiet hours of night, there's something deeply satisfying about the methodical way science approaches such mysteries. The careful accumulation of observations, the patient analysis of data, the gradual building of understanding through hypothesis and verification, all represent humanity at its most thoughtful and collaborative. The story of 3I/ATLAS and its potential connection to the wow signal reminds us that the universe still holds secrets waiting to be discovered. Each night brings new possibilities, new observations, new chances to glimpse the cosmic processes that shape matter and energy across space and time. Whether this particular mystery leads to revolutionary discoveries or merely adds another chapter to our understanding of natural astronomical phenomena, it serves as a reminder of why we look up at the stars with wonder. In a universe filled with billions of galaxies, each containing billions of stars, the possibilities for discovery are truly limitless. As we drift towards sleep, we can take comfort in knowing that patient observers around the world continue their cosmic vigil, watching and waiting for the next revelation to emerge from the darkness between the stars. The universe may keep its secrets well, but human curiosity and ingenuity ensure that eventually, even the deepest mysteries yield to careful investigation and thoughtful analysis. The gentle dance of discovery continues, driven by questions that span generations and powered by the fundamental human desire to understand our place in the cosmic order. In this ongoing quest, objects like 3I/ATLAS serve as guides, leading us toward new understanding of the vast and wondrous universe we call home. Tonight, as 3I/ATLAS continues its ancient journey through the warmth of our inner solar system, we find ourselves witnessing something that touches the very heart of what it means to be human in an infinite cosmos. There's a peculiar intimacy in watching this visitor from another star system as it slowly brightens and develops its ethereal tale, knowing that we may be the only conscious observers in our corner of the galaxy to witness this particular cosmic performance. The comet's gradual transformation from a dark, invisible speck to a glowing beacon speaks to processes that have been unfolding since long before Earth formed. The ices now sublimating in our sun's warmth were condensed from gases that swirled around a different star when our own solar system was nothing more than a faint possibility in a distant molecular cloud. These are waters that have never known terrestrial shores, carbons that have never cycled through earthly life, molecules that carry within their bonds the signature of alien stellar furnaces. As we observe this celestial awakening, it's worth pausing to consider the profound loneliness that 3I/ATLAS has endured during its interstellar passage. For millions of years, it has travelled through space so empty that a handful of atoms might occupy a volume the size of a cathedral. The silence out there is more complete than anything we can imagine on Earth, broken only by the occasional whisper of cosmic rays or the gentle pressure of starlight from distant suns. Yet, in this isolation, the comet has maintained its chemical integrity, preserving within its nucleus a library of information about conditions that existed around another star when our galaxy was younger. Every molecule now streaming from its surface tells a story written in atomic signatures, a narrative of stellar evolution and planetary formation that we're only just beginning to learn how to read. The spectroscopic analysis of 3I/ATLAS continues to reveal compositions that challenge our understanding of how planetary systems form and evolve. The ratios of different isotopes found in its outgassing products suggest nucleosynthetic processes operating under conditions quite different from those that shaped our own solar neighborhood. Heavy elements that are rare in our cosmic vicinity appear in abundance, while others that we consider common seem surprisingly scarce. These chemical fingerprints paint a picture of a stellar environment where the balance of cosmic recycling followed different pathways. Perhaps 3I/ATLAS formed around a star that was part of an earlier generation of stellar formation, when the galaxy's chemical composition was different from what we observe today. Or maybe it originated in a region where supernovae had enriched the interstellar medium with unusual abundances of specific elements. The implications of such chemical diversity extend far beyond academic curiosity. If planetary systems throughout the galaxy form under such varied conditions, then the potential environments for life might be far more diverse than we've imagined. What we consider the normal conditions for planet formation may represent just one small subset of the possibilities that exist throughout the cosmic community. This perspective transforms how we think about the search for life beyond Earth. Rather than looking for planets that closely resemble our own world, we might need to consider biological processes that could operate under very different chemical regimes. Life, if it exists elsewhere, might have learned to thrive using elements and compounds that are rare or absent in terrestrial biology. The study of 3I/ATLAS also illuminates the dynamic nature of galactic evolution. The space between stars isn't empty, but filled with a tenuous medium of gas and dust that serves as both the graveyard and nursery of stellar generations. Objects like our interstellar visitor mix and redistribute this material as they travel, carrying samples from one stellar system to another over cosmic timescales. This process of cosmic cross-pollination has been operating since the first stars began to die and scatter their enriched material into space. Over billions of years, the chemical complexity of the galaxy has gradually increased as successive generations of stars have processed hydrogen and helium into heavier elements. Interstellar objects serve as the messengers in this slow conversation between stellar systems. The trajectory of 3I/ATLAS through our solar system follows paths carved by gravitational forces that operated millions of years ago. Every close encounter with a massive object, every passage through a stellar system's influence, has subtly altered its course. The comet we observe today is the product of countless such interactions, a cosmic billiard ball that has been nudged and deflected by the gravitational architecture of our galaxy. Yet for all the apparent randomness of this process, there's something almost purposeful about the way 3I/ATLAS has timed its arrival. Its approach during an era when humanity possesses the technology to detect and study it seems like a gift from the universe itself. A few centuries earlier, and this visitor would have passed unnoticed through our cosmic neighborhood, its secrets remaining forever hidden. The precision required for such timing becomes even more remarkable when we consider the scales involved. The comet's journey has taken it across distances that light itself requires years to traverse, through regions of space where matter is spread so thin that Earth's atmosphere would seem impossibly dense by comparison. That it should arrive at just the moment when we're prepared to appreciate its significance seems almost too convenient to be mere coincidence. This sense of cosmic timing extends to the potential connection with the WOW signal. If these events are indeed related, they suggest a kind of patience that transcends human understanding. Any intelligence capable of coordinating activities across such temporal and spatial scales would need to think in terms that make our longest-term planning seem like momentary impulses. The psychological impact of contemplating such vast scales can be both humbling and inspiring. On one hand, it reminds us of how brief and fragile our individual existence appears against the cosmic backdrop. On the other hand, it celebrates our remarkable ability as a species to detect and interpret phenomena operating on scales far beyond our direct experience. The fact that we can calculate the precise trajectory of 3I/ATLAS, predict its future path with extraordinary accuracy, and decode the chemical messages written in its spectral lines represents one of humanity's greatest intellectual achievements. We've learned to extend our senses across interstellar distances and our understanding across cosmic timescales, transforming ourselves from terrestrial creatures into cosmic observers. This transformation has been gradual, built through centuries of patient observation and theoretical development. Each generation of astronomers has pushed our understanding a little further, developing new instruments and techniques that reveal previously hidden aspects of the universe. The study of interstellar objects like 3I/ATLAS represents the latest chapter in this ongoing expansion of human awareness. The collaborative nature of modern astronomy makes this expansion possible. No single observatory or research team could capture all the information that 3I/ATLAS might reveal during its brief passage through our solar system. Instead, The scientific community has organized itself into a global network of observers, each contributing specialized capabilities to the collective effort. Radio telescopes scan for any unusual emissions that might echo the mysterious signal from 1977. Optical observatories dissect the comet's light into its component wavelengths, revealing the molecular signatures of compounds that formed around another star. Space-based instruments study its behavior free from atmospheric interference, capturing details invisible from Earth's surface. This coordinated campaign represents humanity at its most cooperative and thoughtful. Political boundaries and cultural differences fade into insignificance when confronted with cosmic mysteries that transcend earthly concerns. The brief passage of an interstellar visitor demands such unity of purpose, creating temporary communities of researchers united by shared curiosity about the universe. The data flowing from these observations will take years to fully analyze and understand. Each spectrum requires careful comparison with laboratory measurements to identify specific molecular species. Chemical abundances must be calculated from emission line intensities. Physical properties need to be inferred from subtle variations in brightness and color. Yet even preliminary results continue to confirm 3I/ATLAS's status as something. Its chemical composition remains genuinely extraordinary, unlike anything we've observed in object's solar system. From our own, its physical behavior reveals processes shaped by interstellar environments we can barely imagine. Every measurement reinforces its identity as an authentic messenger from the depths of space. The broader implications of studying such messengers extend far beyond individual discoveries. These cosmic ambassadors provide our only direct access to materials from other stellar environments, offering insights into processes that operate throughout our galaxy. Each visitor carries information encoded in its chemical composition, physical structure, and orbital characteristics. If interstellar objects prove to be as common as theoretical models suggest, they could revolutionize our understanding of galactic evolution. The systematic study of their chemical signatures might allow us to map how elements have been distributed throughout the Milky Way over cosmic time. We could trace the pathways by which materials produced in stellar cores have spread to create the chemical diversity we observe today. The implications for understanding life's potential distribution are particularly profound. If organic molecules prove to be common in interstellar objects, it would suggest that the chemical foundations of biology operate throughout the galaxy. Complex organic synthesis might occur not just on planetary surfaces, but in the cold depths of interstellar space itself. Such discoveries would transform our perspective on where life might arise and how it might spread between stellar systems. Rather than being confined to individual planets, biological processes might participate in a galaxy-wide network of chemical exchange that operates over millions of years. Life itself might be more nomadic than we've imagined, traveling between star systems aboard cosmic messengers like 3I/ATLAS. The gentle warming of our interstellar visitor as it approaches the Sun provides a real-time laboratory for testing these possibilities. As ancient ices sublimate and create the comet's growing coma, spectroscopic analysis can identify any organic compounds that might be present. Each molecular species detected adds another piece to our understanding of interstellar chemistry. The process of this awakening follows patterns 3I/ATLAS first form established billions of years ago when around its distant parent star. The same physical laws that govern sublimation and outgassing in our solar system operated in that alien environment, creating similar processes under different conditions. Yet the specific details, the ratios of different compounds and the sequence of their release carry information about those foreign circumstances. This universality of physical Rosetta Stone, that law provides a kind of cosmic by interstellar visitors, the messages carry allows us to interpret the universe, making it possible to decode information. The language of physics consistently throughout, and chemistry operates from stellar environments we may never observe directly. Every photon of light, every spectral line, every chemical signature speaks in this universal tongue. The growing brightness of 3I/ATLAS as it approaches perihelion creates a sense of anticipation throughout the astronomical community. This peak of activity will provide the best opportunity to study its composition and behavior in detail. The increased outgassing will reveal inner materials that have been protected from cosmic ray bombardment during the long interstellar journey. Observatories around the world have coordinated their efforts to capture this cosmic crescendo from multiple perspectives. The brief window of maximum activity demands such coordination, as no single facility can observe continuously or across all wavelengths of interest. This international collaboration transforms what might have been a limited local observation into a comprehensive global investigation. The psychological resonance of studying an interstellar visitor extends beyond scientific curiosity into realms of wonder and connection that touch something fundamental about human nature. There's an almost mystical quality to examining material that formed around another star, that has traveled across the galaxy to reach our cosmic doorstep. Each measurement connects us, however tenuously, to stellar environments we can barely imagine. This connection operates on multiple levels simultaneously. Scientifically, 3I/ATLAS provides direct access to materials and processes from distant stellar systems. Philosophically, it reminds us that our solar system exists within a vast galactic community where matter and energy flow between star systems over cosmic time. Emotionally, it evokes a sense of kinship with the larger universe that transcends our terrestrial origins. The comet's approach also highlights the dynamic nature of our cosmic neighborhood. What we often perceive as the stable, unchanging heavens is actually in constant motion, with objects regularly exchanging between stellar systems as our galaxy slowly evolves. Our Sun and its family of planets travel through space at hundreds of kilometers per second, encountering new regions of the interstellar medium as we orbit the galactic center. This motion means that the cosmic environment around Earth is constantly changing on timescales far longer than human civilization. The interstellar medium through which our solar system currently moves has different properties than the regions we occupied millions of years ago or will encounter in the distant future. In this context, the arrival of 3I/ATLAS represents just one moment in an ongoing cosmic conversation. The potential connection to the WOW signal adds layers of mystery that transcend conventional astrophysics. If these events are indeed related, they suggest forms of cosmic activity or communication operating according to timescales that dwarf human experience. A phenomenon that began with a radio signal in 1977 and culminates with a comet's discovery in 2025 would represent coordination across nearly half a century of Earth time. Such temporal coordination challenges our assumptions about how intelligence might manifest in the universe. We tend to think in terms of immediate cause and effect, expecting responses within timeframes meaningful to individual human lives. But cosmic intelligence, if it exists, might operate according to rhythms that span geological ages, planning activities that unfold over millions of years. This perspective transforms our understanding of what extraterrestrial contact might look like. Instead of expecting rapid exchanges of radio messages, we might need to search for patterns that emerge over decades or centuries. The patient accumulation of seemingly unrelated observations might eventually reveal connections that operate on scales far beyond immediate human perception. The blue-shifted frequency of the WOW signal continues to intrigue researchers exploring this potential connection. The apparent motion of the signal source toward Earth at roughly 10 kilometers per second aligns remarkably well with what we might expect from 3I/ATLAS during its approach to our solar system in 1977. This velocity component has long puzzled SETI researchers, as it didn't match any known astronomical object in the Sagittarius region. The discovery of an interstellar object approaching from that same direction provides, for the first time, a plausible explanation for this mysterious Doppler signature. The precision of this match goes beyond simple coincidence, suggesting either extraordinary luck or something more purposeful operating behind these cosmic alignments. The narrow bandwidth of the original signal also takes on new significance when viewed through the lens of modern astrophysical understanding. Most natural radio sources emit across broad frequency ranges, making the precision and focus of the WOW signal highly unusual. Recent theoretical work has identified natural processes that could produce narrowband emissions at the hydrogen frequency, but these require extremely precise alignments of astronomical objects and conditions. Even these sophisticated natural explanations struggle to account for the specific combination of characteristics observed in the 1977 signal. The required coincidences of timing, alignment, and intensity stretch the bounds of statistical plausibility, particularly when combined with the apparent connection to 3I/ATLAS's trajectory. Yet this is precisely where the scientific method proves its value in distinguishing between meaningful patterns and statistical noise. The human brain is exquisitely evolved to detect connections and significance, even in random data. The challenge lies in determining when apparent correlations reflect genuine physical relationships, rather than the inevitable result of pattern-seeking minds examining vast datasets. The response of the scientific community to this potential connection reflects the careful balance between skepticism and open-mindedness that characterizes rigorous research. Most astronomers remain appropriately cautious about drawing firm conclusions from correlational evidence, while acknowledging that the apparent relationship deserves serious investigation and analysis. This measured approach serves science well, preventing premature acceptance of extraordinary claims, while ensuring that genuinely revolutionary discoveries aren't dismissed without proper consideration. The history of astronomy provides numerous examples of observations that initially seemed impossible, but later proved fundamental to our understanding of the universe. As 3I/ATLAS continues its measured approach toward the Sun, each day brings new opportunities for observation and discovery. The gradual increase in solar heating drives more vigorous outgassing, revealing additional details about the comet's internal composition and structure. This slow unveiling creates a sense of anticipation that builds naturally toward the moment of closest approach. The international coordination required to study this brief cosmic event has created temporary communities of researchers united by shared fascination with the unknown. Language barriers and cultural differences fade into insignificance when confronted with questions that transcend earthly concerns. The passage of an interstellar visitor reminds us that we're all inhabitants of the same small planet, sharing the same cosmic neighborhood. This perspective can be profoundly transformative for those who contemplate it deeply. The realization that we exist within a vast galactic community, that matter and energy regularly flow between stellar systems, that we're connected to cosmic processes operating on unimaginable scales, can shift our understanding of humanity's place in the universe. Such insights don't diminish human significance, but rather expand our sense of participation in something much larger and more enduring than terrestrial affairs. We become not just inhabitants of Earth, but citizens of the galaxy, participants in cosmic processes that have been unfolding since the first stars began to shine billions of years ago. The gentle passage of 3I/ATLAS through our solar system thus represents more than just an astronomical event. It offers a moment of connection across the vast emptiness of space. A reminder that we live in a universe filled with wonders that challenge our understanding and expand our sense of what's possible. As we drift towards sleep, contemplating these cosmic mysteries, we can take comfort in knowing that patient observers continue their vigil throughout the night. Somewhere, telescopes are tracking the comet's progress across the sky. Somewhere, Computers are processing spectroscopic data that might reveal new secrets about interstellar chemistry. Somewhere, researchers are comparing new observations with theoretical predictions, gradually building our understanding of the galaxy beyond our solar system. The story of 3I/ATLAS and its potential connection to that famous signal from 1977 reminds us that the universe operates according to rhythms far grander than human timescales. What appears to us as separate, isolated events might actually be part of larger patterns that become apparent only when viewed from the proper temporal perspective. Whether this cosmic coincidence represents something profound or merely the statistical inevitability of rare events occurring in an infinite universe, it invites us to consider how discovery itself unfolds across time. The astronomers who first detected the WOW signal had no way of knowing that decades later, an object would be discovered approaching from the same region of sky. Similarly, those studying 3I/ATLAS today cannot predict what connections future observations might reveal. This uncertainty is perhaps one of the most beautiful aspects of scientific inquiry. We build our understanding incrementally, observation by observation, never quite knowing when the next measurement might transform our entire perspective on the cosmos. The universe seems to delight in presenting us with puzzles that require patience and persistence to solve, if indeed they can be solved at all. The methodical accumulation of knowledge proceeds according to its own gentle rhythm, driven by human curiosity and powered by our fundamental desire to understand the cosmic order. Each night brings new possibilities, new observations, new chances to glimpse the processes that shape matter and energy across the galaxy. In this ongoing quest for understanding, objects like 3I/ATLAS serve as guides, leading us toward new insights about the vast and wondrous universe we inhabit. Whether they carry messages from distant civilizations or simply represent the natural workings of cosmic processes, they expand our awareness and deepen our appreciation for the mysteries that surround us. The gentle dance of scientific discovery continues, measured in decades and centuries rather than moments, guided by questions that span generations and powered by the enduring human capacity for wonder. As we settle into sleep, we can rest assured that this cosmic conversation will continue, that somewhere in the darkness, between the stars, new revelations are making their way toward our small corner of the galaxy, carrying secrets that will inspire future generations of cosmic explorers. The dance between observation and interpretation continues as 3I/ATLAS draws ever closer to its moment of maximum revelation. There's something deeply meditative about the way astronomical discovery unfolds, requiring patience that spans not just individual nights but entire seasons of careful watching. Each measurement builds upon the last, creating a mosaic of understanding that emerges pixel by pixel, spectrum by spectrum, until suddenly we find ourselves looking at something entirely unexpected. The comet's behavior, as it approaches the inner solar system, follows patterns that are both familiar and alien. Like any icy body subjected to increasing solar radiation, it develops the characteristic coma and tail that mark its passage through space. Yet the details of this awakening reveal processes shaped by conditions we've never encountered before, chemistry that speaks of stellar environments operating under different rules than those that governed our own cosmic origins. Modern spectroscopic techniques allow us to eavesdrop on conversations between atoms and molecules that began billions of years ago. Every photon captured by our detectors carries information encoded at the quantum level, signatures written in the universal language of physics that remain constant whether they originate in our solar neighborhood or in stellar systems thousands of light years away. It's this consistency that makes interstellar archaeology possible, allowing us to decode messages written in wavelengths of light. The isotopic signatures emerging from 3I/ATLAS's analysis tell stories of stellar nucleosynthesis, operating under conditions quite different from those that created the elements in our own bodies. The ratios of different atomic variants suggest formation around a star that burned hotter and faster than our Sun, or perhaps in a region where multiple generations of stellar death and rebirth had created unusual abundances of heavy elements. These chemical fingerprints provide direct evidence for the diversity of stellar environments that exist throughout our galaxy. What we consider normal conditions for planetary formation may represent just one small sample of the possibilities that exist in the cosmic community. The implications for understanding where life might arise become profound when we consider how dramatically different chemical starting points might lead to biological processes we've never imagined. The trajectory calculations for 3 I/ATLAS continue to reveal the remarkable precision of celestial mechanics. Despite the apparent randomness of galactic dynamics, where countless gravitational influences nudge objects along complex pathways, the comet's arrival in our solar system follows mathematical laws that allow us to predict its future path with extraordinary accuracy. This predictability provides a kind of cosmic anchor in an uncertain universe, reminding us that beneath the apparent chaos lies an underlying order we can understand and appreciate. The growing international collaboration surrounding 3 I/ATLAS observations represents one of humanity's finest expressions of cooperative curiosity. Research teams from different continents share data in real time, combining observations from radio telescopes in remote deserts with spectroscopic measurements from mountaintop observatories. Language barriers dissolve when confronted with universal questions about the nature of matter and motion in the cosmos. This global coordination becomes especially important as the comet approaches its closest point to the Sun. The window of maximum observational opportunity lasts only weeks, demanding that every available instrument be brought to bear on this fleeting chance to study materials from another stellar system. The brief nature of the encounter transforms what might otherwise be a leisurely investigation into an intensive campaign of discovery. Each night brings new revelations as 3 I/ATLAS continues to brighten and develop its spectacular tale. The outgassing products streaming from its nucleus create a laboratory in space where we can observe chemical processes that have been dormant for millions of years. Ancient ices sublime directly into the vacuum of space, carrying with them molecular fossils that preserve information about conditions that existed when our galaxy was younger. The emotional resonance of studying such phenomena extends far beyond academic interest. There's something profoundly moving about the realization that we're examining materials older than our solar system itself, substances that formed around a different star, when our own cosmic neighborhood was nothing more than a sparse collection of gas and dust. Each molecule detected in the comet's tail represents a direct connection to stellar processes that operated under alien skies. This sense of connection operates on multiple levels simultaneously. Scientifically, 3 I/ATLAS provides unprecedented access to materials from distant stellar environments. Philosophically, it reminds us that our solar system participates in a vast galactic ecosystem where matter flows between star systems over cosmic timescales. Personally, it evokes a kind of cosmic homesickness for places we've never been, but somehow recognize as part of our larger heritage. The potential relationship between this interstellar visitor and the famous radio signal from 1977 continues to intrigue researchers willing to consider unconventional possibilities. The temporal separation between these events, spanning nearly half a century of human time, challenges our assumptions about how cosmic phenomena might unfold. If these occurrences are indeed connected, they suggest coordination operating on scales that such transcend individual human lifespeed possibilities require us to expand our thinking about how intelligence might manifest in the universe. The rapid communication we take for granted in terrestrial affairs becomes meaningless when applied to interstellar distances and cosmic timescales. Any civilization capable of coordinating activities across such vast scales in terms of geological would need to think ages rather than seasonal cycles. The precision required for such coordination becomes even more remarkable when we consider the gravitational choreography involved in guiding an object across interstellar space with sufficient accuracy to arrive at a predetermined location millions of years later. The mathematical complexity of such calculations would challenge even our most sophisticated computational capabilities, requiring knowledge of galactic dynamics that we beginning to understand. Yet their only alternative explanation, that we're witnessing an extraordinary series of coincidences, requires its own form of mathematical improbability. The alignment of trajectories, the matching of velocities, the correspondence of timing, all create a pattern that occurs by chance less frequently than we might expect in a truly random universe. This statistical tension between coincidence and causation lies at the heart of many astronomical mysteries. The blue shift detected in the original WOW signal provides one of the most intriguing pieces of this cosmic puzzle. The apparent motion of the signal source toward Earth at roughly 10 kilometers per second has long puzzled researchers, as no known astronomical object in the Sagittarius region exhibited such velocity characteristics. The discovery of 3 I/ATLAS approaching from that same direction with compatible motion provides the first plausible explanation for this mysterious Doppler signature. This velocity matching represents more than simple numerical agreement. It suggests a physical relationship between two phenomena separated by decades of time, but potentially connected by origin. The precision of this correspondence goes beyond what we might expect from random astronomical events, hinting at underlying patterns that operate on scales larger than individual human observation. The narrow bandwidth of the 1977 signal also takes on new significance when viewed through modern understanding of astrophysical radio sources. Most natural phenomena that produce radio emissions do so across broad frequency ranges, making the focused nature of the WOW signal highly unusual. The discovery of an interstellar object with compatible trajectory and timing provides context for interpreting this precision. Recent theoretical advances have identified natural processes that could produce narrow emissions at the hydrogen frequency, but these band radio mechanisms require extraordinary alignments of astronomical objects and environmental conditions. Even the most sophisticated models struggle to account for the specific combination of characteristics observed in both the radio signal and the interstellar visitor. The accumulation of unusual features in this cosmic narrative creates a pattern that challenges conventional explanations while remaining within the bounds of physical possibility. This tension between the extraordinary and the explicable represents one of the most fascinating aspects of modern astronomical research, where theoretical models must stretch to accommodate observations that push the boundaries of statistical expectation. The ongoing analysis of 3 I/ATLAS continues to reveal characteristics that set it apart from any object previously studied. Its chemical composition remains unlike anything observed in our solar system, while its physical behavior reflects processes shaped by interstellar environments we can barely comprehend. Every measurement reinforces its status as a genuine messenger from the depths of galactic space. The broader implications of such discoveries extend far beyond individual astronomical events. These cosmic ambassadors provide our only direct access to materials from other stellar systems, offering insights into planetary formation processes that operate throughout the galaxy. Each visitor carries information encoded in its composition, structure, and trajectory that illuminates conditions existing elsewhere in our cosmic neighborhood. If interstellar objects prove as common as theoretical models suggest, they could revolutionize our understanding of how matter and energy flow between stellar systems. The systematic study of their chemical signatures might eventually allow us to map the distribution of elements throughout the galaxy, tracing pathways by which materials produced in stellar cores have spread to create the chemical diversity we observe today. The implications for astrobiology become particularly profound when we consider the possibility that organic molecules might be common in such cosmic wanderers. If complex organic chemistry operates not just on planetary surfaces but throughout interstellar space itself, it would suggest that the chemical foundations of life participate in a galaxy-wide network of exchange that operates over millions of years. Such discoveries would fundamentally alter our perspective on where life might arise and how biological processes might spread between stellar systems. Rather than being confined to individual planetary environments, the chemistry of life might be inherently nomadic, traveling between star systems aboard cosmic messengers like 3I/ATLAS, and participating in evolutionary processes that span the entire galaxy. The gentle warming of our interstellar visitor as it approaches the Sun creates a natural laboratory for testing these possibilities. As ancient ices begin to sublime and release their molecular contents, spectroscopic analysis can identify any organic compounds that might be preserved within the comet's nucleus. Each chemical species detected adds another piece to our understanding of how complex chemistry operates in the cosmic environment. This process of gradual revelation follows rhythms established billions of years ago when 3I/ATLAS first condensed from the primordial material surrounding its parent star. The same physical laws that govern phase transitions and molecular behavior throughout the universe operated in that distant environment, creating processes that we can recognize and interpret even across the vast gulfs of space and time. The universality of physical law provides the foundation for this cosmic communication. Chemistry and physics operate consistently throughout the universe, creating a kind of natural language that allows us to decode information from stellar environments we may never observe directly. Every spectral line, every isotopic ratio, every chemical signature speaks in this universal tongue that transcends the boundaries between stellar systems. The growing brightness of 3I/ATLAS, as it approaches its closest point to the Sun, has created mounting anticipation throughout the global astronomical community. This peak of activity represents the optimal moment for studying the comet's composition and behavior in unprecedented detail. The increased outgassing driven by solar heating will reveal materials from the object's interior that have been protected from cosmic ray bombardment throughout its interstellar journey. Observatories spanning multiple continents have synchronized their efforts to capture this cosmic crescendo from every possible perspective. The brief duration of maximum activity demands such comprehensive coordination, transforming what might have been isolated local observations into a unified global investigation. This international collaboration exemplifies humanity's capacity for cooperation when confronted with questions that transcend terrestrial boundaries. The data flowing from these coordinated observations will require months or years of careful analysis to fully understand. Spectroscopic measurements must be calibrated against laboratory standards to identify specific molecular species. Chemical abundances need calculation from emission line intensities. Physical properties must be inferred from subtle variations in brightness, color, and temporal behavior. Yet even preliminary results continue to confirm the extraordinary nature of our interstellar visitor. Each measurement adds weight to its identity as something genuinely foreign to our solar system, carrying chemical signatures and physical characteristics that reflect formation in environments unlike anything we've previously studied. The systematic accumulation of evidence builds a portrait of an object that challenges our understanding while expanding our knowledge of what's possible in the cosmic environment. The psychological impact of studying materials from another star system resonates on frequencies deeper than scientific curiosity alone. There's an almost mystical quality to examining substances that formed around a different sun, that have journeyed across the galaxy to reach our cosmic doorstep. Each photon of reflected light connects us, however tenuously, to stellar processes that operated under alien skies when our own world was young. This connection transcends the merely academic, touching something fundamental about human nature and our relationship with the larger universe. We become not just observers of cosmic phenomena, but participants in galactic processes that have been unfolding since the first stars began to shine. The realization that we exist within a vast community of stellar systems, where matter regularly flows between different worlds, transforms our understanding of humanity's place in the cosmic order. The dynamic nature of our galactic neighborhood becomes apparent through observations of visitors like 3I/ATLAS. What we often perceive as stable and unchanging heavens actually represent a complex dance of matter and energy operating on timescales far longer than human civilization. Our entire solar system travels through space at tremendous velocity, encountering different regions of the interstellar medium as we orbit the galactic center over periods of hundreds of millions of years. This motion ensures that the cosmic environment around Earth changes continuously on geological timescales. The interstellar conditions we experience today differ from those our solar system encountered in the past, and will differ again from those we'll meet in the distant future. In this context, the arrival of interstellar objects represents ongoing cosmic conversation between stellar systems as they exchange materials across the galaxy. The potential connection between 3I/ATLAS and the WOW signal adds dimensions of mystery that extend beyond conventional astrophysical interpretation. If these phenomena are indeed related, they suggest forms of cosmic activity or communication that operate according to planning horizons spanning multiple human generations. Any intelligence capable of coordinating events across such temporal scales would think in ways fundamentally different from terrestrial consciousness. This perspective challenges our assumptions about how extraterrestrial contact might manifest. Rather than expecting immediate exchanges of information, we might need to search for patterns that unfold over decades or centuries. The patient accumulation of seemingly unrelated observations might eventually reveal connections that operate on scales far beyond immediate human perception, requiring institutional memory and collaborative effort spanning multiple generations of researchers. The narrow bandwidth and precise frequency of the original radio signal continue to puzzle researchers exploring these potential connections. Most natural astrophysical phenomena produce radio emissions across broad frequency ranges, making the focused nature of the 1977 detection highly unusual. The correspondence between this precision and the calculated trajectory of 3I/ATLAS during that same period creates correlations that extend beyond simple statistical coincidence. Even sophisticated natural explanations for narrowband hydrogen line emissions require extraordinary alignments of cosmic objects and environmental conditions. The probability of such alignments occurring naturally becomes even more remote when combined with the trajectory calculations that place 3I/ATLAS in the appropriate region of space during the relevant time frame. The accumulation of low probability events creates patterns that challenge conventional interpretation. Yet, this is precisely where scientific methodology proves its value in distinguishing between meaningful correlations and the inevitable patterns that emerge when pattern-seeking minds examine sufficiently large data sets. The human brain evolved to detect significance and connection, even in random information, creating a constant challenge for researchers attempting to separate genuine discoveries from wishful thinking. The measured response of the scientific community to these potential connections reflects the careful balance between skepticism and openness that characterizes rigorous inquiry. Most researchers remain appropriately cautious about drawing firm conclusions from correlational evidence, while acknowledging that unusual patterns deserve serious investigation. This balanced approach prevents premature acceptance of extraordinary claims, while ensuring that genuinely revolutionary insights aren't dismissed without proper consideration. The history of astronomical discovery provides numerous examples of observations that initially seemed impossible, but later proved fundamental to our understanding of the universe. From the counterintuitive implications of planetary motion to the bizarre properties of quantum mechanics, scientific progress often requires accepting ideas that challenge common sense and conventional wisdom. As 3I/ATLAS continues its stately progression toward the inner solar system, each passing day brings new opportunities for observation and discovery. The gradual increase in solar heating drives more vigorous outgassing, revealing additional details about the comet's internal structure and composition. This slow unveiling creates natural drama as researchers worldwide wait to see what secrets this ancient wanderer might reveal during its brief moment of maximum visibility. The international coordination required to study this fleeting cosmic event has created temporary communities of researchers united by shared fascination with the unknown. Cultural differences and national boundaries become irrelevant when confronted with questions that transcend earthly concerns. The passage of an interstellar visitor remino all inhabitants us that we of the same small world, sharing the same cosmic neighborhood and participating in the same quest for understanding. This perspective can profoundly shift how we think about humanity's place in the universe. The realization that we exist within a vast galactic community, that matter flows regularly between stellar systems, that we're connected to cosmic processes operating on unimaginable scales, expands our sense of identity beyond terrestrial boundaries. We become citizens not just of Earth, but of the galaxy itself, participants in evolutionary processes that span billions of years. The gentle passage of 3I/ATLAS through our solar system thus represents far more than a mere astronomical curiosity. It offers a moment of connection across the emptiness of interstellar space, a reminder that we inhabit a universe filled with wonders that challenge understanding and expand our conception of what's possible. Whether this visitor carries messages from distant civilizations or simply represents the natural workings of cosmic processes, it deepens our appreciation for the mysteries surrounding us. As night settles around the world and telescopes turn toward the brightening comet, we can find comfort in knowing that patient observers continue their vigil. Somewhere, instruments are tracking its progress across star fields. Somewhere, computers process spectroscopic data that might reveal new aspects of interstellar chemistry. Somewhere, researchers compare fresh observations with theoretical predictions, gradually building our collective understanding of the galaxy beyond our solar system. The story unfolding around 3I/ATLAS and its potential relationship to phenomena from decades past reminds us that the universe operates according to rhythms far grander than human timescales. What appears to us as isolated events might actually represent chapters in larger narratives that become apparent only when viewed from proper temporal perspective. The patient accumulation of observations across multiple generations of researchers may eventually reveal patterns that individual human lifespans are too brief to perceive. Whether this cosmic coincidence represents something profound or merely statistical inevitability in an infinite universe, it invites contemplation of how discovery itself unfolds through time. Scientists who first detected that famous radio signal could never have predicted that decades later, an object would be found approaching from the same celestial region. Similarly, those studying our current interstellar visitor cannot anticipate what connections future observations might illuminate. This uncertainty embodies one of the most beautiful aspects of scientific inquiry. We construct understanding incrementally, measurement by measurement, never knowing when the next observation might transform our entire perspective. The universe delights in presenting puzzles that require patience and persistence to solve, if they can be solved at all. The methodical accumulation of knowledge proceeds according to its own rhythm, driven by curiosity and sustained by our fundamental desire to comprehend the cosmic order. Each night that passes brings 3I/ATLAS closer to its moment of greatest revelation, that singular point in its million-year journey when our sun's warmth will coax forth the deepest secrets held within its ancient nucleus. There's something almost ceremonial about this approaching culmination, as if the universe itself has orchestrated this cosmic unveiling for our benefit. The comet's steady brightening creates a natural countdown, marking days until perihelion with the precision of a celestial clock. The increasing activity observed in recent weeks has begun to reveal layers of complexity that weren't apparent during the visitor's initial detection. As solar radiation penetrates deeper into the nucleus, it liberates gases that have been trapped since the comet's formation billions of years ago. Each new spectral line that appears tells another chapter of the story, adding molecular characters to a narrative written in the language of atoms and ions. The most recent observations have detected trace amounts of exotic compounds that challenge our understanding of interstellar chemistry. Molecules containing unusual isotopic ratios suggest nucleosynthetic processes operating under conditions quite different from those that shaped our local cosmic environment. These chemical fingerprints speak of a stellar nursery, where the balance of elements followed pathways unknown in our solar neighborhood, creating compositions that seem almost deliberately crafted to intrigue and perplex. The outgassing patterns themselves reveal internal structures unlike anything observed in objects native to our solar system. The way different compounds are released as the comet warms suggests a layered composition that records the varying conditions present during its formation. Like reading tree rings or geological strata, these temporal signatures preserve information about the environment that existed around a distant star when our own world was nothing more than cosmic dust. The collaborative nature of studying 3I/ATLAS has created an unprecedented example of global scientific cooperation. Research teams from every inhabited continent share data in real time, creating a continuous observation network that follows the comet around the clock. As Earth rotates, different observatories take up the watch, ensuring that no significant developments escape notice during this critical period of approach. This international effort has revealed details that no single observatory could have captured alone. Radio telescopes in remote locations scan for unusual emissions, while optical facilities on mountain peaks dissect the comet's light into component wavelengths. Space-based instruments provide perspectives free from atmospheric interference, capturing subtleties invisible from Earth's surface. The synthesis of these varied observations creates a portrait far richer than any individual dataset could provide. The technological sophistication required to decode messages written in starlight represents one of humanity's most remarkable achievements. Modern spectrographs can identify individual molecular species in the comet's tail with precision that would have seemed magical to earlier generations of astronomers. We've learned to read the cosmic correspondence carried by photons that have travelled alongside this ancient wanderer for part of its interstellar journey. Each molecule detected adds another piece to our understanding of how matter behaves in the cosmic environment. The preservation of complex compounds during millions of years of interstellar travel demonstrates the remarkable stability that can exist in the apparent emptiness between stars. What seems like hostile vacuum actually provides a kind of deep freeze that maintains chemical integrity across vast distances and enormous spans of time. The emotional resonance of this discovery extends far beyond academic interest into realms that touch something fundamental about human consciousness. There's an almost spiritual quality to realizing that we're examining materials older than our entire solar system, substances that witnessed the galaxy when it was younger and chemically simpler than the universe we know today. Every analysis connects us directly to stellar processes that operated under alien skies. This connection operates simultaneously across multiple dimensions of understanding. Intellectually, 3I/ATLAS provides unprecedented access to materials from distant stellar environments, expanding our knowledge of planetary formation throughout the galaxy. Emotionally, It evokes a profound sense of kinship with cosmic processes that dwarf human experience, yet somehow include us as conscious participants in their unfolding. The visitor's approach has also illuminated the dynamic nature of our galactic neighborhood in ways that static observations of distant objects cannot match. We're witnessing in real time how matter flows between stellar systems, how the galaxy mixes and redistributes the elements created in stellar furnaces over billions of years. This cosmic recycling operates on scales that challenge human comprehension while following physical laws we can understand and predict. The potential relationship between this interstellar wanderer and the radio anomaly from 1977 continues to intrigue researchers willing to consider possibilities beyond conventional astronomical explanation. The temporal span separating these events, nearly half a century of human experience, suggests coordination operating on scales that transcend individual lifespans and require institutional memory spanning multiple generations. Such possibilities demand that we expand our thinking about how intelligence might manifest across cosmic distances and timescales. The rapid communication we consider normal in terrestrial affairs becomes meaningless when applied to interstellar coordination. Any civilization capable of planning activities across such vast scales would need to think in terms of geological ages rather than seasonal cycles, developing patience that exceeds human comprehension. The mathematical precision required for such coordination becomes staggering when we consider the gravitational choreography involved in guiding an object across interstellar space with sufficient accuracy to arrive at predetermined coordinates millions of years later. The computational complexity of such calculations would challenge our most sophisticated systems, requiring detailed knowledge of galactic dynamics that we're only beginning to develop. Yet the alternative explanation that we're witnessing an extraordinary sequence of coincidences carries its own burden of statistical improbability. The alignment of trajectories, the correspondence of velocities, the matching of temporal patterns, all combine to create correlations that occur by pure chance less frequently than we might expect in a truly random universe. This tension between coincidence and causation lies at the heart of many astronomical mysteries. The frequency characteristics of the original radio detection provide one of the most compelling aspects of this cosmic puzzle. The apparent blue shift indicating motion toward Earth at roughly 10 kilometers per second has puzzled researchers for decades, as no known object in the Sagittarius region exhibited compatible velocity signatures. The discovery of 3I/ATLAS, approaching from that same celestial region with matching motion, provides the first plausible explanation for this long-standing mystery. This velocity correspondence represents far more than numerical agreement. It suggests a physical relationship between phenomena separated by decades of time, but potentially united by common origin. The precision of this match extends beyond what random astronomical events would typically produce, hinting at underlying patterns that operate on scales larger than individual human observation can easily encompass. The narrow bandwidth of the 1977 signal also gains new significance when interpreted through modern understanding of astrophysical radio sources. Most natural phenomena that generate radio emissions do so across broad frequency ranges, making the focused characteristics of that famous detection highly unusual among known astronomical events. The temporal correlation with 3I/ATLAS provides context for understanding this remarkable precision. Recent advances in theoretical astrophysics have identified natural mechanisms that could produce focused radio emissions at the hydrogen frequency. But these processes require extraordinary alignments of cosmic objects and environmental conditions. Even the most sophisticated models struggle to account for the specific combination of characteristics observed in both the radio anomaly and our current interstellar visitor. The accumulation of unusual features in this unfolding narrative creates patterns that challenge conventional explanation, while remaining within the boundaries of physical possibility. This tension between the extraordinary and the explicable represents one of the most fascinating aspects of contemporary astronomical research, where theoretical frameworks must stretch to accommodate observations that push the limits of statistical expectation. The ongoing analysis of 3I/ATLAS continues revealing characteristics that distinguish it from every object previously studied in our cosmic neighborhood. Its chemical composition remains unlike anything observed among solar system natives, while its physical behavior reflects processes shaped by interstellar environments we can only imagine. Each new measurement reinforces its identity as an authentic messenger from the galactic depths. The broader implications of such discoveries reach far beyond individual astronomical events into realms that could transform our understanding of how the galaxy operates. These cosmic ambassadors provide our only direct access to materials from other stellar systems, offering insights into planetary formation processes throughout our galactic community. Each visitor carries information encoded in composition, structure, and trajectory that illuminates conditions existing in distant stellar neighborhoods. If interstellar objects prove as common as theoretical models suggest, they could revolutionize our comprehension of how matter and energy circulate between stellar systems. The systematic study of their chemical signatures might eventually allow mapping the distribution of elements throughout the galaxy, tracing pathways by which materials forged in stellar cores have spread to create the chemical diversity we observe in our cosmic environment. The implications for understanding life's potential distribution become particularly profound when we consider that organic molecules might be common passengers aboard such cosmic wanderers. If complex organic chemistry operates not merely on planetary surfaces, but throughout the interstellar medium itself, it would suggest that biological foundations participate in a galaxy-wide network of chemical exchange operating over millions of years. Such revelations would fundamentally alter our perspective on where life might emerge and how biological processes could spread between stellar systems. Rather than being confined to individual planetary environments, the chemistry underlying life might be inherently nomadic, traveling between star systems aboard messengers like 3I/ATLAS and participating in evolutionary processes that span the entire galaxy. The gentle warming of our visitor as it approaches the Sun creates a natural laboratory for testing these profound possibilities. As ancient ices begin subliming and releasing their molecular contents into space, spectroscopic analysis can identify any organic compounds preserved within the comet's nucleus. Each chemical species detected adds crucial information to our understanding of how complex chemistry operates in the cosmic environment. This process of gradual revelation follows rhythms established when 3I/ATLAS first condensed from material surrounding its distant parent star. The same physical laws governing phase transitions and molecular behavior throughout the universe operated in that alien environment, creating processes we can recognize and interpret even across the vast expanses of space and time that separate us from its origin. The universality of physical law provides the foundation for this cosmic communication spanning stellar distances. Chemistry and physics operate consistently throughout the universe, creating a natural language that allows decoding information from stellar environments we may never observe directly. Every spectral signature, every isotopic ratio, every chemical fingerprint speaks in this universal tongue that transcends boundaries between different stellar systems. The brightening of 3I/ATLAS as it approaches its closest solar encounter has generated mounting excitement throughout the global astronomical community. This peak of activity represents the optimal window for studying the comet's composition and behavior with unprecedented detail. The enhanced outgassing driven by increasing solar heating will reveal materials from deep within the object's interior that have remained protected from cosmic ray bombardment throughout the interstellar journey. Observatories spanning continents have synchronized their efforts to capture this cosmic crescendo, from every conceivable perspective. The brief duration of maximum activity demands such comprehensive coordination, transforming what might have been isolated local studies into a unified global investigation. This international collaboration exemplifies humanity's finest capacity for cooperation when confronted with questions that transcend terrestrial boundaries and national concerns. The data streams flowing from these coordinated observations will require extensive analysis to fully comprehend. Spectroscopic measurements must undergo calibration against laboratory standards to identify specific molecular species with confidence. Chemical abundances need calculation from emission line intensities measured across multiple wavelength ranges. Physical properties must be inferred from subtle variations in brightness, color, and temporal behavior patterns. Yet even preliminary results continue confirming the extraordinary nature of our interstellar guest. Each measurement adds evidence supporting its identity as something genuinely foreign to our solar system, carrying chemical signatures and physical characteristics reflecting formation in environments unlike anything previously studied. The systematic accumulation of evidence constructs a portrait of an object that challenges understanding while expanding knowledge of cosmic possibilities. The psychological impact of studying materials from another stellar system resonates on frequencies deeper than scientific curiosity alone can explain. There's an almost mystical dimension to examining substances that formed around a different sun, that have journeyed across galactic distances to reach our cosmic doorstep. Each reflected photon connects us, however tenuously, to stellar processes that operated under foreign skies when our own solar system was young. This connection transcends mere academic interest, touching something essential about human nature and our relationship with the larger cosmos. We become more than simple observers of astronomical phenomena, transforming into active participants in galactic processes that have been unfolding since the first generation of stars began illuminating the universe. The realization that we exist within a vast community of stellar systems where matter regularly circulates between different worlds fundamentally alters our understanding of humanity's place in the cosmic hierarchy. As we settle deeper into contemplation of these cosmic mysteries, there's profound comfort to be found in the methodical way scientific understanding develops. The patient accumulation of observations, the careful analysis of data, the gradual construction of knowledge through hypothesis and verification all represent humanity expressing its most thoughtful and collaborative nature. Whether 3I/ATLAS proves to carry messages from distant civilizations or simply represents natural cosmic processes in operation, it expands our awareness and deepens appreciation for the wonders surrounding us. The story continues unfolding as this ancient wanderer makes its stately way through our solar system, carrying within its nucleus the accumulated history of stellar processes that operated when the galaxy was younger. Each night brings new observations, new spectra, new opportunities to decode the cosmic correspondence written in wavelengths of light. The universe may guard its secrets carefully, but human curiosity and ingenuity ensure that eventually, even the most profound mysteries yield to patient investigation and thoughtful analysis. The gentle rhythm of cosmic revelation continues as we approach the culmination of our journey through this extraordinary tale of signals and wanderers. As 3I/ATLAS draws ever closer to its moment of greatest visibility, astronomers around the world maintain their patient vigil, knowing that this fleeting encounter represents a once-in-a-lifetime opportunity to peer into the chemical heart of an object that has traveled between the stars for millions of years. There's something deeply moving about the way this cosmic visitor has timed its arrival, as if the universe itself were orchestrating a grand performance for our benefit. The steady brightening creates a natural crescendo, each night revealing new details about composition and behavior that challenge our understanding of how matter survives the harsh journey through interstellar space. The outgassing patterns emerging from recent observations suggest internal structures unlike anything we've encountered before, layered compositions that preserve the history of conditions existing around a distant star when our own solar system was merely a possibility. The collaborative spirit surrounding these observations has created something beautiful, a temporary global community united by shared wonder at phenomena that transcend earthly concerns. Language barriers and cultural differences dissolve when confronted with questions about the fundamental nature of matter and motion in the cosmos. This international cooperation represents humanity at its finest, demonstrating our capacity for working together when inspired by mysteries that dwarf our individual perspectives. As the comet continues its ancient dance through our cosmic neighborhood, it carries with it secrets that may reshape our understanding of how the galaxy operates. Whether these secrets point toward natural processes we've never encountered or something more extraordinary remains to be seen. But in either case, 3I/ATLAS has already succeeded in expanding our sense of what's possible in this vast and wondrous universe we call home. The gentle passage of time that separates the famous signal from decades past and this current visitor reminds us that cosmic stories often unfold according to rhythms far grander than human experience. What appears to us as separate events might actually represent chapters in larger narratives that become apparent only when viewed from the proper temporal perspective. In this ongoing conversation between Earth and cosmos, we remain both students and participants, forever learning from messengers that arrive from the darkness between the stars. So as we drift toward the peaceful embrace of sleep, we can rest knowing that somewhere in the night sky, this ancient traveler continues its journey, carrying within its nucleus the accumulated wisdom of stellar processes that have been shaping matter and energy since the first stars began to shine. The universe may keep its deepest secrets well hidden, but human curiosity ensures that each generation pushes a little further into the mystery, adding new chapters to our ever-expanding story of cosmic understanding. Sweet dreams, fellow travelers, wherever and whenever you find yourselves in this grand cosmic dance we all share together. And so, dear listener, we find ourselves at the end of this gentle voyage through the cosmic mystery that connects a famous radio whisper from 1977 with an ancient wanderer now gracing our solar system. We've explored the mathematical precision of celestial mechanics, the chemical fingerprints of distant stellar nurseries, and the profound questions that arise when two extraordinary phenomena seem to dance together across the vast stages of space and time. Whether 3I/ATLAS carries within its nucleus the secrets of natural cosmic processes operating on scales we're only beginning to understand, or something more extraordinary that challenges our assumptions about intelligence in the universe, it has already given us something precious, a reminder that we live in a cosmos filled with wonders beyond our current comprehension. The wow signal, and this interstellar visitor, separated by decades yet potentially connected by origin, invite us to remain curious, to keep watching the skies, and to hold space for possibilities that might initially seem beyond the realm of the probable. As this ancient traveler continues its journey toward the warmth of our sun, carrying with it the accumulated story of stellar processes that operated when the galaxy was younger, we can take comfort in knowing that patient observers around the world will continue their vigil. Each spectrum captured, each chemical signature decoded, each observation shared across the global community of cosmic explorers adds another piece to the grand puzzle of our place in the universe. The gentle dance of scientific discovery continues, measured not in moments but in generations, powered by the enduring human capacity for wonder. Whether we're witnessing an extraordinary coincidence or something more profound, this cosmic tale reminds us that in a universe filled with billions of galaxies, each containing billions of stars, the next great revelation might be approaching even now through the darkness between worlds, waiting patiently for curious minds to notice its arrival. Sleep well, knowing that the cosmos continues its patient work of revelation, and that somewhere in the vast night, new mysteries are making their way toward our small corner of the galaxy. In the vast night, New mysteries are making their way toward our small corner of the galaxy.